We're going to get very deep into deep learning. But before we get started, I want to take a minute and look at the big picture and put deep learning into context. I want to present 4 distinct analytical challenges. First, we have a basic scatter plot. Second, a scatter plot containing a third binary variable. Third, we have a medical scan of a knee joint. And finally, we see a photograph. I think of these as different analytical challenges because the research questions that you, as a statistician or data scientist, ask will be context specific. So will your analytical methods and, of course, the results or the answer to your research question. But I want to make the argument that if we step back a bit, we'll see that we treat all of these problems in the same way. What we're doing is simply trying to make sense of the world by looking for patterns in various representations. We look at these representations and match the patterns we see to a huge catalog of patterns that we've accumulated over years of experience. So although we'll use different analytical methods on each data set, I'd also argue that many techniques in data science are doing the same thing. We're trying to find patterns in these different kinds of data. For example, for our simple scatter plot, we may want to know what is the best model that describes the relationship between 2 variables. How do we draw this relationship? And how objective is it? What are the subjective decisions that were made? Are there alternative models? Should we consider groupwise models? And can our models be predictive? In the second scatter plot, the question is a bit different. Here, we may be interested in knowing what model separates the 2 groups defined by the third binary variable. Although the mathematical process is different, the result serves a similar purpose. We have a representation of the real world, and we want to use that to generate some model that accurately reflects the relationship between these variables. To that end, the best model is a combination of objective maths, subjective experience, and domain expertise. Although I didn't go into detail, data scientists will be familiar with the techniques depicted here. Okay, but what about those pictures? And what does any of this have to do with deep learning? Well, it's kind of the same story. We're still just trying to find patterns in these examples. For example, a doctor would look at the image of a knee joint and look for fractures or unusual patterns. Or we'd look at the picture of a cat and realize that, well, it's a cat. So again, depending on the data, we ask different questions. For a picture, what or who is it? Is there something unusual happening? We're still just looking for patterns. The major topics in data science, such as classification, regression, clustering, dimensional reduction, and shallow forms of machine learning, just take different approaches to look for those patterns. The technique we use is determined by the type of data available and the research question at hand. So where does deep learning fit into all of this? Deep learning sits in the artificial intelligence arena of the data science landscape and can be understood as a specialized form of machine learning. We can see deep learning as an extension of the ideas we're already used to, but the way we build models here is going to be a little bit more complex. You can probably imagine that that's necessary since we're trying to answer more sophisticated questions. For example, if we want to classify a picture as a dog or a cat, we basically have a binary classification problem. Here are some actual examples of images from a classification problem using computer vision that we'll tackle in the second part of the course. Notice that the pictures are not consistent in size, resolution, or image orientation. There are many approaches to tackle binary classification. Some of the most basic methods are decision trees or logistic regression. They both allow us to predict a binary response variable according to some predictor variable. You can probably appreciate that a much more subtle and nuanced model is needed for a binary classification involving computer vision. It's simply because the input data is inherently more complex and noisy, and we need models that can handle that. Picture or facial recognition is another example. Can a computer identify what's in a picture? And if there's a person, how old are they? These are 2 examples from Google and Microsoft. Some of the biggest technology companies are working on developing deep learning methods and applications. And it's not just the big companies. DeepL is a competitor to Google Translate. And remember that example of the knee joint? That's an application of deep learning to medical images. Can you imagine the huge potential benefit to being able to automatically identify patterns in CAT scans, fMRI images, X-rays, or mammograms? Could computers identify patterns that until now we've missed? So deep learning is an elaborate extension of the pattern recognition concepts that we're already familiar with in data science. But deep learning can handle much more complex data and find much more subtler patterns. Before we end this video, there's one more thing that I want to mention. So far, all the examples we've looked at have simply taken some representation of the real world and produced a model to describe the underlying pattern. But deep learning can go further. It can actually generate data, as shown in this example. These are actual pictures of people, and these are pictures of people generated by deep learning. Some of them are a bit off, but it's remarkably good already. Deep learning is already contributing to content creation, and its role in this area has a potential for immense growth. For example, Google can now use generative techniques on Street View images to produce beautiful landscape images. As I mentioned at the beginning of this unit, deep learning has achieved breakthroughs in many historically difficult areas of machine learning. Even though the name deep learning is relatively new, researchers have been working on these methods for decades. Nonetheless, the field has only recently been made widely accessible to a broad audience of statisticians and data scientists. One of the great advantages of deep learning is that the complexity of feature engineering is greatly reduced. So although the algorithms are more complex and may take longer to train, that means it's easier to get up and running if you have the proper resources. This is a great time to get familiar with deep learning, and I'm happy to see you in this course.